To interpret the effect that an explanatory variable has on our response variable in a Poisson regression model, we do not use odds ratios. Rather, we end up using something that is formulated in a very similar way. So to help see what this measure is, let's take a look at a Poisson regression model with only one explanatory variable. So we have the exponential function evaluated at beta 0 plus beta 1 times x. And just for emphasis, I'm going to put on the left side not just mu, but mu of x, to say that this the mu, or the mean, is a function of x, our explanatory variable. Now we could then also use or look at the model where we have a c unit increase in x. So again, we see c there. So now we have mu of x plus c. And let's form a ratio of these two different cases. When we do that, notice what happens. Some stuff cancels out, and we're left with the exponential function evaluated at c times beta 1. Very similar to what we had with a logistic regression model or even other model where we had a c unit increase in our x, and we were looking at odds ratios. So this then leads to a convenient way to interpret the effect that x has on our response. The percentage change in the mean response that results from a c unit change in x is what I call PC, which is equal to 100 times the exponential function evaluated at c times beta 1 minus 1. This PC stands for percentage change. So just to give you a quick little example of what this means, let's say that the exponential function evaluated at c times beta 1 is equal to 1.1. What this means then for us, that PC is equal to 10%. So a key thing here is that notice that our expression is not dependent upon the value of x itself. What's important is that c unit increase, just like what we saw with odds ratios. Of course, one needs to choose an appropriate value of c for the problem of interest. The estimated PC value is as what you would expect. Just put a hat on top of the beta and also put a big hat over the PC. We can do walled and likelihood ratio confidence intervals with this. If there's more than one explanatory variable in the model, we again include an additional statement such as holding all the other variables in the model constant. We can include interactions, we can include transformations in here with the same kinds of changes as what we've seen previously for the interpretation of odds ratios. So let's take a look at an example. So we're going to go back to the horseshoe crab example, and let's say we let c be equal to 1 centimeter. Then a 1 centimeter increase in the width leads to a 17.83% increase in the mean width, estimated increase in the mean width. So I guess the formal interpretation then would be the percentage change in the estimated mean number of satellites that results from a 1 unit change in width is 17.83%. You can use this interpretation here essentially as a template for your own interpretations. So other ways to phrase this as well include a 1 unit increase in width leads to an estimated 17.83% increase in the mean number of satellites. The mean number of satellites is estimated to increase by 17.83% for every 1 centimeter increase in the width of the shell. So we see some differences here include the emphasizing that we have an increase. So you can use then again these interpretations as well for templates for your own interpretations for other problems of interest. Now, is c equal 1 centimeter appropriate for this particular data? And that's difficult to say. I'm not an expert on horseshoe crabs. But whenever you're faced with a situation where you're not necessarily for sure what c should be, you can always go to a 1 standard deviation change in that x value. So if we did that, I could use the SD function R to find one standard deviation for, or find the standard deviation for the width of the crabs, and I get 2.1. If I put that in there and it's something called C dot unit, multiply it by my beta hat 1, do the corresponding calculation, then actually it's a little bit off there. Sorry, I forgot some parentheses. Let me just double check that real fast. Here's my corresponding code. Yep, and I forgot those parentheses just in the notes. And I get a value of 41.34. So what that means in terms of this particular problem, a 2.11 centimeter increase in width leads to a 41%, an estimated 41% increase in the mean number of satellites. Well, what about now doing confidence intervals? Well, we could do profile likelihood ratio intervals, and we do it basically the same way that we've seen previously with a logistic regression model. So for example, we first find a confidence interval for the beta 1 itself. And so I use the confident function, object equal mod.fit. I'm interested in just width itself, 95% interval for beta 1. Then I use this little mathematical equation here where I take 100 times the quantity of that exponential function evaluated at c times beta hat 1, c is 1. I'm going to go back to c equal 1, and then I subtract off 1. So what that says then here is that my confidence interval is 13.28% to 22.51%. We can use we can also use, the MC profile package as well to do this, again in much the same way as what we've seen for odds ratios relative to a logistic regression model. Of course, with this, with MC profile, we need to find this K matrix. Again, our PC value is only dependent upon beta 1 itself. So in my K matrix, I have a 0 as the coefficient for beta 0, and then I have a 1 as the coefficient for beta 1. I have a 1 row, 2 column matrix. I use the MC profile package, MC profile function to calculate negative 2 log lambda. Then I use the method function corresponding to confint in the MC profile package to find the confidence interval for beta 1. And then lastly, I do this transformation of the lower limit and the upper limit, much the same way that we've done before. And here is my confidence interval, 13.28 to 22.5. And notice how these two match. So I guess the official interpretation would be with 95% confidence. A 1 unit increase in width leads to a 13.3% to 22.5% increase in the mean number of satellites. We could also do walled confidence intervals as well. I'll let you look at some of the details here on your own. We again use confident.default, like what we did for logistic regression. We can do a walled interval using, let's say, the actual mathematical expression by programming it into R as well. And then lastly, we can do a walled interval using EM means, and that's what I do want to take some time to discuss. The code here is very similar to what we saw before with logistic regression. So first of all, I say EM means my model fit information is in mod.fit. For the specs argument, I only put the explanatory variable of interest. And then I need to say, well, which values am I interested in for this explanatory variable? And so I create a list to do that, where I say width is equal to 31 and 30. Now, if you remember when we worked with like the place kicking data set and we were working with distance, to work in this particular situation, I don't have a way to specify C itself. So the way that I essentially specify C is in this at argument where I separate my two different values of my explanatory variable by C units. C is equal to 1 here, so that's why I chose 31 and 30. Because 31 is listed first, this will go in the numerator of my PC calculation. 30 will go in the denominator. when I take the part of the calculation where I have the ratio of those two means. I could have used, let's say, 26 and 25. I could have used 36 and 35. The key is you have to have that C unit change between the two different values. I then say type equal response. Then I use the contrast function so that it can do some calculations here with calc.s that's saved from em means. Method equals, I want pairwise comparisons. In this case, allows me to do the comparison between 31 and 30. Then finally, I use the confidence function. My level is 95%. And so here in the results, we can see that I have with 31 in the numerator, with 30 in the denominator. This ratio is e to the 1 times beta hat 1. This confidence interval is a confidence interval for e to the beta 1. Now, of course, we don't want, that's not our PC value exactly. So what we can do is just ourselves apply this transformation that we've seen, that 100 times e to the beta 1 minus 1. And so we can see that my walled confidence interval for PC is 13% to 23%. So some comments. I kind of just explained this. EMEs doesn't provide us an exact way to get to the PC value itself. Instead, we can just simply look at this and say, okay, I see a 1.13 there, so I know it's 13% is the lower bound. And I've already talked about this other comment as well. Okay. Well, what about if we have categorical explanatory variables and we want to include them in the model and then interpret them? And as you might guess what I'm going to say next, it's very similar to what we have for odds ratios for logistic regression models when we had categorical explanatory variables. So you might remember this particular example where we had a 4-level categorical explanatory variable with levels A through D. By default, R will assign A as the base level. So all comparisons are essentially being made to that automatically. We could have our we could have our Poisson regression model as log of mu is equal to beta 0 plus beta 1 times then the indicator function corresponding to B plus beta 2 times the indicator function corresponding to C. And lastly, plus beta 3 times the indicator variable corresponding to D. And so if we look at the PC value, where we use the exponential function evaluated at beta 1 inside of it, this gives us a comparison, or the percentage change, from going from B to A. B's in the numerator, A's in the denominator. Remember, a common mistake that sometimes people make is that they would think that this would be a comparison of B to all the levels. No, it's only B to the baseline level. You can make similar statements about C to A, where you would have e to the beta 2 in there. D to A, where you would have the exponential function evaluated at beta 3 there. If I wanted to make other kinds of comparisons, such as B to C, just like what we did with odds ratios, I strongly recommend you actually write out the ratio part so that you can see, for example, you would need the exponential function evaluated beta 1 minus beta 2 in the PC calculation. Please make sure you can do that on your own. Okay, so this then concludes this section that looks at the percentage change measure as a way to interpret the effect that an explanatory variable has on the response variable.